The boiler room clock reads 7:30 when Thomas Harwell pulls the main steam valve. The hiss echoes through the workshop like a final exhale, long, wet, fading into nothing. Above him, the great iron pipes begin their nightly ritual of contraction, ticking and groaning as metal cools degree by degree. Down on the factory floor, the belt system starts its descent into silence. The main drive belt, 30 feet of leather and canvas, thick as a man's wrist, loses tension first. It sags between its pulleys, still moving but slowing, the slap, slap, slap against the guides growing lazy. One by one, the machines surrender. The planers stop biting. The lathes coast to stillness. The punch press gives one final clunk and goes quiet. This is the sound every mill worker knows. The sound of work ending. The sound of going home. Except tonight, something stays awake. William Chen notices it first. He's 23, been working the night cleanup crew for 8 months, and he's learned to read the rhythms of this place the way sailors read the sea. He's sweeping metal shavings near the old gear train when he feels it, a vibration through the floorboards. Subtle, wrong. He stops, listens. The main line shaft should be dead by now. The steam's been cut for 4 full minutes, but somewhere in the mechanical darkness, something is still turning. Chen walks toward the sound, his lantern throwing shadows across the belt housings and all-stained workbenches. The light catches it about 20 feet away, the secondary transfer gear. Massive thing, maybe 5 feet across, cast iron teeth the size of your thumb. It's mounted to the line shaft at chest height, positioned to drive the metalworking section when the whole system's under power. And it's rotating, slowly, deliberately, clicking past its housing mount once every 3 seconds. Click, click, click. Chen's throat goes dry. He calls for Harwell. The foreman arrives with 2 other workers, their boots heavy on the wooden planking. Nobody speaks at first. They just stand there in a half-circle, watching this thing that should not be moving continue its patient revolution in the lamplight. Wind from outside, someone offers. Harwell shakes his head. No windows on that shaft, and it's enclosed. Maybe the belt's still. Look at the belt. They look. The drive belt hangs limp, barely touching the pulley. No tension, no grip. Nothing that could move a gear this size even an inch, let alone drive it through continuous rotation. The gear keeps turning. Chen reaches out, stupid move, he'll realize later, and presses his palm against the iron rim. The metal is warm, not from recent work, but from some internal momentum he can feel through his skin. The gear doesn't stop. It pushes against his hand with the kind of patient, terrible strength that machines have when they're under power. Except there is no power. He jerks back. Shut it down, someone says. Jam it, something. Harwell just stares. In 17 years running industrial floors, he's seen belt breaks and shaft failures, and one catastrophic flywheel explosion that painted the east wall red. But he's never seen a machine refuse to stop. The gear turns through the night. When the crew finally leaves, spooked, exhausted, trying to laugh it off, they can still hear it from the street. Click, click, click. By morning, 5 men will refuse to work the floor. The next night, Chen arrives early. He wants to see it in daylight first, wants to prove to himself that it's just, what? A trick of exhaustion. Bad oil in the bearings. He doesn't know, but he needs it to make sense. The gear is stopped, completely still. He stands there for 5 minutes, watching. Nothing. When the day shift fires up the main boiler and the whole system lurches into motion, the gear behaves exactly as it should. It spins under load, drives its section, transfers power down the line like it's done for 3 years without complaint. But that night, after shutdown, it starts again. This time it's worse. The gear doesn't just turn, it accelerates, slowly but measurably. Chen times it with his pocket watch. At 7:45, the gear is making 1 rotation every 5 seconds. By 8:00, it's down to 4. By 8:30, down to 3. Then, just after 9 o'clock, it stops. Dead stop. No coasting, no gradual slowdown. Just stopped like someone threw a brake. 10 minutes later, it starts again. Same direction, same patient, purposeful rotation. Word spreads. By the third night, there are 12 men gathered around the gear train after shutdown, watching like it's a stage performance. Some bring notebooks, others bring whiskey. Harwell tries to maintain order, but you can see the unease in his face. This isn't how machines work. Machines obey. They start when you start them and stop when you stop them. They don't have moods. On the fourth night, something new. The gear starts moving before shutdown. The main steam is still on, the drive belt is under full tension, everything's running hot and loud the way it should be. But the gear, the secondary transfer gear that everyone's now watching obsessively, suddenly jerks against its normal motion. Just once. A single tooth width of reverse rotation, then back to normal. 3 men see it happen. 2 of them will quit by the end of the week. The rumors start simple. Sabotage, obviously. Someone's rigged a secondary drive, a hidden mechanism, a prank to spook the night crew. Harwell orders a full inspection. They pull the belt housing, check the shaft bearings, examine every connecting rod and coupling within 10 feet of the gear. Nothing. No hidden springs, no wound mechanisms, no clever leverage that could explain autonomous motion. The rumors grow teeth. "It's a warning," says Marcus Webb, a layout man who's worked here since the building opened. "Machines know when they're gonna break. This whole line shaft's gonna come apart and kill someone." "Machines don't know anything," Harwell snaps, but his voice carries less conviction than it did 3 days ago. "Then explain it." Harwell can't. By the end of the first week, the gear has developed a pattern. It stops during the day. It moves at night. Sometimes fast, sometimes slow. Sometimes for hours, sometimes for minutes. And occasionally, maybe twice, it reverses direction entirely, turning backwards against the line shaft orientation, which shouldn't be possible without breaking the mounting or stripping the teeth. Tools left on nearby benches start vibrating when the gear moves. A wrench. A file. Once, an entire toolbox walks 3 inches across a workbench before someone grabs it. The night crew begins to thin. Men find excuses. Sick wives, bad backs. One guy just stops showing up, never collects his final pay. The ones who stay do so out of something that isn't quite bravery and isn't quite stubbornness. It's the need to know. The human inability to walk away from a mystery, even when the mystery feels dangerous. Chen is one of them. Every night he arrives with his lantern and his notebook, recording times and speeds and temperatures. He doesn't believe in ghosts. He believes in mechanisms, which means somewhere in this pile of iron and leather and wood, there's an answer. He just has to find it before someone gets hurt. To understand what's happening, you have to see the whole system. The workshop is a cathedral of motion, or it was, before the fear set in. The main drive shaft runs the entire length of the building, 90 feet of forged iron 3 inches thick, mounted on cast brackets every 8 feet. It's the spine of everything. When the boiler's hot and the steam engine's running, this shaft spins at maybe 180 revolutions per minute, and from it, everything else draws power. Hanging from the ceiling, the belt system spreads like a web. Flat belts, round belts, crossed belts that reverse direction. They drop from the main shaft to individual machines. Lathes here, drill presses there, a massive planer in the corner that can smooth a 6-foot iron plate in one pass. Each machine has a clutch system, a way to engage or disengage from the moving belt without stopping the whole line. It's elegant in its way, but it's also complicated. There are maybe 40 connection points, 20 machines, a dozen subsystems, and buried in that complexity, the secondary transfer gear. This gear isn't special by design. It's just a power relay meant to take motion from the main shaft and redirect it to the metalworking section at a different height. 5 feet in diameter, maybe 120 teeth, keyed to a smaller parallel shaft that runs perpendicular to the main drive. What makes it special is the flywheel. Not the gear itself, though it's heavy. but the massive iron flywheel mounted to the same shaft, maybe 10 feet away. Nobody remembers exactly when it was added. The installation records say 1881, but the handwriting's unclear and the original foreman is dead. What's clear is that someone wanted rotational stability on this section. The flywheel weighs maybe 800 pounds, solid cast iron, 4 feet across, spokes as thick as your forearm. Flywheels store energy. That's their job. When the system's under power, they smooth out vibrations, keep rotation steady even when loads vary. They're the reason a punch press doesn't stall when it punches, or a lathe doesn't judder when cutting threads. But they're also batteries, mechanical batteries. And when you spin 800 pounds of iron up to speed, it doesn't want to stop. Chen figures this out on day 6. He's lying on his back under the shaft, lantern beside him, staring up at the bearing mounts. The gear is turning again, slow tonight, maybe one rotation every 6 seconds. But if he shifts his focus, if he ignores the gear and watches the shaft itself, he can see it. The whole parallel shaft is rotating. Not much, not fast, but it's moving, and the flywheel is moving with it. It's not the gear, he says aloud. It's the flywheel. Harwell is standing above him, arms crossed. What? The gear's just the part we can see, but the energy's in the flywheel. That thing's been spinning all day under load, and when we shut down, it just keeps going. 4 hours. Maybe. That's not possible. But even as Harwell says it, he's doing the math in his head. Mass times velocity, rotational inertia. He's not an engineer, none of them are, but he knows machines, and he knows that heavy things don't stop easy. They climb back up to the floor and approach the flywheel. It's enclosed in a partial housing, wooden panels meant to keep hands and clothing away from the spokes. Through the gap, you can see it turning. Slow, smooth, almost serene. Chen presses his hand against the housing. The vibration is clearer here, more purposeful. The wood hums. Bearings, Harwell says suddenly. If the bearings are that smooth, if there's almost no friction, it could coast for hours. They stare at each other. It's not a complete answer. There are still the speed changes, the reversals, the sudden stops. But it's the first explanation that doesn't require ghosts. Over the next 2 days, they map the system. Every belt, every connection, every bearing mount. They discover that the parallel shaft connects to 3 separate machines, each with its own clutch mechanism. They discover that one of the belt runs crosses another belt at an odd angle, creating intermittent contact. They discover that the main shaft has a slight wobble, barely perceptible during operation, but may be significant during shutdown. And they discover something else. At night, when the building cools, the belt tensions change. Leather shrinks when it cools. Canvas tightens. The massive drive belts that hang loose during the day pull tighter as the temperature drops, and a tight belt on a smooth pulley can transmit torque even when it's not supposed to. Not much. Not enough to drive a machine under load. But maybe enough to nudge a flywheel that's already coasting. The pieces start to fit. The mystery begins to crack. But it's not over yet. The explanation doesn't calm anyone. If anything, it makes things worse. So you're saying, Marcus Webb says slowly, that this whole system is just doing what it wants, that we shut it down but it keeps running anyway. Not running, Harwell corrects. Coasting, there's a difference. Feels the same from where I'm standing. He's not wrong. Knowing the mechanics doesn't change the experience. The gear still turns in the dark. The flywheel still hums through the night. And now there's a new fear. If the system can store this much energy, if it can run unsupervised for hours, what happens when something goes wrong? The incident happens on a Tuesday. James Yao, metalworker, 15 years in the trade, decides he's had enough. He arrives during shutdown, marches straight to the gear train, and pulls a 4-foot pry bar from the tool rack. I'm stopping it, he announces. Don't, Chen starts, but Yao's already moving. He jams the pry bar into the gear teeth, leveraging against the shaft housing. For a moment, nothing happens. The gear keeps turning, patient and unstoppable. Then the bar bites. Metal screams. The gear doesn't stop. It jerks, twists, and the pry bar whips sideways with enough force to tear itself out of Yao's hands. The bar flies across the workshop and embeds itself in a wooden support beam 20 feet away, vibrating like a tuning fork. Yao stumbles back, hands bleeding, face white. The gear turns 3 more rotations, then stops. Everyone stares, at Yao, at the bar, at the gear which sits motionless now as if nothing happened. Jesus Christ, someone whispers. Harwell orders everyone out. He stands alone in the workshop for 10 minutes, just looking at the system, at this thing they've built and operated and taken for granted. Somewhere in his mind, a calculation is running. How much force did that bar experience? How much energy is actually stored in that flywheel? And most importantly, could it kill someone? Yes, he realizes, easily. By Wednesday, the local newspaper picks up the story. They send a reporter, a young guy with ink-stained fingers and a notepad, who interviews workers outside the building. The article runs Friday under the headline, "The Haunted Workshop of Millbrook Street." It's meant to be sensational, a bit of fun. But the article includes details: the turning gear, the flying pry bar, the workers who have quit. And it includes speculation. Perhaps the machines of our modern age contain forces we do not yet fully understand. The article makes everything worse. Now it's not just the night crew who are spooked. Day shift workers start requesting transfers. Management begins asking questions. Insurance assessors schedule visits. The whole operation, which has run profitably for years, starts to crack under the weight of a mystery that shouldn't exist. At night, after shutdown, the gear continues its routine. Sometimes turning, sometimes stopped, always unpredictable. Chen keeps his vigil. He's moved a chair near the gear train, and he sits there with his notebook, recording everything. Temperatures, belt tensions, rotation speeds. He's building a data set looking for patterns. On Saturday night, he hears something new. It's past midnight. The gear has been still for 40 minutes. The building is cold now, properly cold, and Chen's breath fogs in the lantern light. He's about to give up, head home, when he hears it. Tap, tap, tap. Metal on metal, rhythmic, coming from somewhere deeper in the machine system. He stands, holds the lantern high, tries to locate the source. The tapping continues. It's not loud, but it's clear, deliberate, like someone's signaling. Then the gear starts moving again. Chen watches it accelerate from stillness to full rotation in maybe 15 seconds. But this time, he's not watching the gear. He's watching the belt. The main drive belt, which has been hanging loose all night, is suddenly taut. Not fully engaged, there's no power source, but taut, like something is pulling it. He follows the belt line with his eyes, tracing it up to the main shaft, across to a connecting pulley, and then he sees it. Another machine, a drill press 20 feet away, is rotating. Just its chuck, just the spindle barely visible in the darkness. But it's moving, and the belt connecting it to the main shaft is under tension. The system isn't isolated, it's all connected. And at night, when everything cools and contracts and settles, the whole web of machines begins a slow, uncoordinated conversation. One machine releases stored energy, which travels through a belt to another shaft, which nudges a flywheel, which drives a gear, which tensions another belt. It's not one ghost, it's a dozen, all talking to each other through iron and leather. Chen writes this down. His hand is shaking. By the second week, they bring in someone who knows. His name is Arthur Pembroke, a mechanical engineer from the capital, 46 years old, with a reputation for solving industrial mysteries. He's consulted on mill failures, analyzed bridge collapses, testified in court about machinery accidents. If anyone can explain the gear, it's him. He arrives on a Monday morning, carrying a leather case full of instruments, calipers, levels, bearing gauges, tension meters. He doesn't speak much, just nods to Harwell and gets to work. For 3 days, he measures everything. He measures the main shaft diameter, exactly 3.2 inches. He measures the bearing clearances, 0.008 inches, tighter than standard. He measures the flywheel weight, actually 920 pounds, heavier than anyone thought. He measures belt tensions, pulley alignments, shaft straightness. He crawls under machines, climbs on top of machines, peers into gaps that haven't been inspected since installation. And on Thursday afternoon, he gathers everyone in the workshop and explains what's happening. The gear isn't the problem, he starts. The gear is just the symptom. The real issue is the entire system and how it was designed, or rather, how it wasn't designed. He pulls out a drawing, rough but clear, showing the lined shaft and its connections. This workshop was built in stages. The main shaft was installed first in 1879. The metalworking section was added in 1881, which is when they added the parallel shaft and the flywheel. Then, in 1883, someone extended the parallel shaft to connect 3 additional machines. Each addition made sense on its own, but nobody looked at the system as a whole. He points to the flywheel. This flywheel stores approximately 45,000 foot-pounds of energy when spinning at full speed. That's enough to lift a horse 10 feet in the air. When you shut down the steam, that energy doesn't disappear. It bleeds off slowly through friction, air resistance, bearing friction, belt drag. In a typical system, it would drain in maybe 2 or 3 minutes. But, Harwell prompts, but your bearings are exceptional. Whoever installed them used a bronze alloy with graphite impregnation. Very smooth, very expensive. Friction coefficient is maybe 1/10 of standard bearings, which means that flywheel can coast for an hour, maybe longer if conditions are right. Someone in the back mutters, Jesus. Pembroke continues. The speed changes you've observed are caused by belt interactions. As the building cools at night, your leather belts contract. A contracting belt increases tension, which means a loose belt that was slipping during the day might grab at night. When a belt grabs, it transmits torque. Not much, maybe 5 or 10% of normal power, but enough to affect a coasting flywheel. He moves to another part of the drawing. The sudden stops happen when internal clutch mechanisms engage randomly. Several of your machines have spring-loaded clutches that can catch when the shaft reaches certain rotation speeds. They're designed to prevent backwards motion during operation, but at coasting speeds, they become unpredictable. And the reverse rotation, Chen asks. Pembroke smiles just slightly. That's the clever part. You have 2 belt crossings in this system, places where one belt passes over another. When both belts are moving, it's fine. But when one belt is still and the other is moving, there's friction between them. That friction can reverse the direction of torque transmission. Essentially, a stopped belt can pull on a moving belt, creating backwards rotation. He lets that sink in. The tapping sound is thermal contraction. Iron contracts as it cools. Your shaft housings are mounted to wooden beams, and wood contracts differently than iron. As the temperature drops, the shafts shift slightly in their mounts, maybe 1/100th of an inch. That creates the tapping. The alignment changes also create small bursts of resistance that speed up or slow down the coasting rotation. Harwell looks around the room. Men are nodding, some reluctantly, some with visible relief. So it's not, someone starts. Haunted? No, it's just physics. Complex physics, admittedly. The kind of physics that emerges when you have dozens of moving parts interacting in ways the designers didn't anticipate. Your system has become what we call mechanically resonant. It has behaviors that arise from the interaction of components, not from any single component's design. Can we fix it? Of course. Replace the bearings with standard friction bearings. Add positive stops to the clutch mechanisms. Retension or replace the belts. Realign the shaft housings with thermal expansion in mind. Any one of those changes would probably solve it. All of them together would definitely solve it. He closes his notebook. But I'll tell you something interesting. This system you've built, accidentally, incrementally, without planning, is actually quite sophisticated. the energy storage, the distributed motion, the adaptive coupling through belt tensions. Engineers are starting to design systems like this on purpose, for smoothness and efficiency. You just built one by accident and then got scared of it. The room is quiet. It's not alive, Pembroke says, but it is smarter than you thought. The teardown begins on a Saturday. They bring in a maintenance crew, proper mechanics with block and tackle, and they systematically disassemble the parallel shaft system. The flywheel comes down first. It takes 6 men and a crane. Then the gear, which is lighter than expected, maybe 300 pounds instead of the 500 everyone assumed. With everything exposed, the wear patterns tell a story. The bearings are, as Pembroke said, exceptionally smooth, but they're also misaligned. Not much, maybe 2 degrees off true, but enough that the shaft has been running at a slight angle for years. That misalignment created uneven loading, which wore the bearing surfaces in an asymmetric pattern, which created small pockets where oil could pool and reduce friction even further in certain positions. Essentially, the shaft had favorite angles, positions where it could rotate almost freely and other positions where it met resistance. During normal operation under power, this was invisible, but during coasting, it created the speed variations everyone had observed. The clutch mechanisms are even more revealing. 2 of the 3 connected machines have clutches that were installed backwards. They work fine under power. The force of rotation is strong enough to override the design error. But at coasting speeds, the springs engage randomly, creating the sudden stops. And the belt crossings. Well, Pembroke was right. There are 2 places where belts overlap, and someone at some point had installed leather belt dressing, basically oil, to prevent squeaking. But oil makes belts slippery, which meant they could slip against each other in ways they weren't supposed to, creating reverse torque. It's a comedy of errors. Dozens of small mistakes, none fatal on their own, but collectively creating a system that behaved like it had a mind of its own. By Monday, the fixes are complete. New bearings, standard friction alloy, corrected clutches, rerouted belts that don't cross, better housing mounts with thermal expansion joints. They run a test, steam up, full power, normal operation, everything works perfectly, then shutdown. The gear coasts for maybe 40 seconds, then stops. Dead stop, silent, the way it's supposed to be. Chen stands there with his notebook, watching the stillness, and he feels something unexpected, disappointment. Miss it? Howell asks, walking up beside him. Maybe. Yeah, me too. They'd solved the mystery, tamed the machine, made the workshop safe again, but something's been lost. That feeling of standing next to something that seemed almost alive, that operated according to rules no one fully understood. It had been frightening, but it had also been remarkable. The workers return. Production resumes. Within a month, the whole incident becomes a story people tell at shift change, embellished slightly, the fear now safely in the past. But Chen keeps his notebooks, pages of measurements, observations, theories. He keeps them because he understands something the others maybe don't. The gear wasn't special. Every machine in this building, every factory in the city, contains the same potential for unexpected behavior. They're all complex systems, built incrementally, maintained imperfectly, operating at the edge of what their designers understood. Most of the time, that complexity stays hidden. The machines do what they're told, but occasionally, under the right conditions, the physics emerges. The systems reveal themselves, and for a moment, humans are forced to confront the fact that they've built things more sophisticated than they realized. The gear that wouldn't stop turning wasn't a ghost. It was just a machine, being more than it was supposed to be. There's a photograph that survives from that workshop. Black and white, slightly blurred, taken by the newspaper reporter who covered the story. It shows the gear train before the teardown, the massive iron gear, the belt housings, the shaft mounts. And in the corner, barely visible, you can see William Chen with his notebook, standing watch. The caption, written in neat script on the back, reads, "The haunted workshop, 1891. But that's not quite right. The workshop was never haunted. It was just misunderstood. And that misunderstanding reveals something important about the age they were living through. The late 19th century was a period of mechanical explosion. Factories were being built faster than engineers could properly design them. Systems were assembled from parts ordered out of catalogues, installed by men who understood their individual trades: carpentry, metalworking, steam fitting, but not necessarily the complex interactions between them. The result was a landscape full of machines that behaved in ways their builders didn't anticipate: flywheels that stored too much energy, belt systems that transmitted force in unexpected directions, resonance effects that made buildings vibrate, thermal expansions that changed everything when the sun went down. Most of the time, these behaviors were minor quirks, things you learn to work around, but occasionally they were dramatic enough to seem supernatural. The gear that wouldn't stop turning wasn't unique. There are records from this period of similar incidents. A printing press in Boston that would spontaneously start running at 2 a.m. A mill in Pennsylvania where the grindstone would reverse direction during shutdown. A locomotive in Ohio whose driving wheels would continue rotating for 30 minutes after the boiler was emptied. All of them had mechanical explanations. All of them scared people first. Because here's the thing about the Industrial Revolution that doesn't make it into the textbooks. It was built on partial knowledge. The mathematics of thermodynamics were still being worked out. The science of materials was mostly empirical. And the engineering of complex systems, the kind of systems thinking that could predict emergent behaviors, really exist yet. People were building machines they didn't fully understand, operating them successfully through experience and intuition, and then occasionally being shocked when the machines did something unexpected. The fear was rational. These were genuinely dangerous systems. A flywheel with 45,000 foot-pounds of stored energy could kill you if it failed. A belt under unexpected tension could take your arm off. The workers who refused night shifts weren't cowards. They were responding appropriately to a system that had revealed itself to be less controlled than anyone thought. But what makes the story of the gear interesting, what makes it worth remembering, is the response. Not the panic, which was understandable, but the investigation. Chen and his notebook, Harwell bringing in Pembroke, the systematic documentation and analysis, the refusal to accept "it's just strange" as an answer. That impulse, the need to understand rather than simply fear, is what ultimately made the Industrial Revolution work. Yes, machines were built on partial knowledge, but when they misbehaved, people didn't abandon them. They studied them, measured them, figured them out, and then built the next generation a little smarter. The gear taught them something, about bearings and flywheels and belt tensions, yes, but also about complexity, about how systems can be greater and stranger than the sum of their parts, about how the most frightening mysteries often have prosaic explanations if you're willing to look. It's easy, from our perspective, to feel superior. We have computers now, finite element analysis. We can model these systems before we build them, predict their behaviors, design out the unexpected. But we're not that different. We're building AI systems we don't fully understand, networks that exhibit emergent behaviors, algorithms that surprise their creators. And occasionally, late at night, when something we built does something we didn't expect, we feel that same cold shock that Chen felt standing in front of the turning gear. The question is the same. Is it alive? Or is it just doing what physics demands in ways we haven't mapped yet? Usually, it's the latter. Usually. The gear doesn't turn anymore. The workshop was demolished in 1923, replaced by a warehouse, then a parking lot. Chen's notebooks were lost. Pembroke's report survives in a technical journal, but almost nobody reads it. But somewhere in the history of how humans learn to live with machines, there's a lesson in that workshop on Millbrook Street. A lesson about respecting complexity, about the gap between what we build and what we understand, about the difference between ghosts and physics. The gear that wouldn't stop turning was never a ghost. It was just the future, arriving before anyone had words for it. And that, in its own way, is more remarkable than any haunting could ever be.